Hello class 10. Today we'll continue with chapter sound, and in that we'll start with sound 7b, that is natural damped and forced vibrations. So we will discuss today the three types of vibrations: natural vibrations or free vibration, forced vibration and damped vibrations. So there are three types of vibrations: natural vibration or free vibrations, damped vibration and forced vibration. Natural vibration is the periodic vibration of a body in the absence of any external force on it, are called natural or free vibrations. The periodic vibrations depends on the shape and size of the body. The time period of the body is called its natural period, and the frequency is called its natural frequency. The fourth thing which is very much common in natural and free vibration is that it always occurs in vacuum. The resistive force is absent. There is no external force in this natural or free vibrations. The vibration continues till infinite times. Once a force is applied, once a simple pendulum we have taken and we have started the motion of the bob and we have left it in vacuum, hence the motion will continue at infinite time, because we are not using another time the external force to stop it. So there is no resistive force in the vacuum. So amplitude also remains same in natural and free vibration, and frequency is fixed for each object. Now we'll discuss all these points one by one. So this is a displacement time graph of a natural or free vibration. In a displacement time graph for a natural and free vibration, the amplitude is same. This is the amplitude. The amplitude is same for natural and free vibrations. There is no change in the amplitude. Whether it is we are drawing this graph, if we are considering a simple pendulum, suppose here we have the bob and it swings towards the one end and the other end, suppose left end and the right end. So the maximum distance it travels, that is the A amplitude. So the amplitude remains constant in a natural or a free vibration. There is no resistive force. What happens if we swing a pendulum over here? After certain time it stops, because the external force, the resistive force is acting over there, and hence when resistive force is more than the applied force, after certain time the pendulum stops. But in vacuum it does not stop because there is no resistive force. Hence the natural vibrations are those vibrations which is a periodic vibration and it happens in the absence of external force, and the body will not stop once it started its vibrations. Okay, the frequency is also fixed for each object. I am explaining it with the formula. Suppose we will consider a case of a simple pendulum. We know that this is the length, the distance of this string with which the bob is suspended. So this is denoted as L, and from 9 you know the formula of the time period of a simple pendulum is 2 pi under root L by G. We know that frequency is equal to 1 by T. Hence when we substitute the value of T, time period, in this formula, we get the relation as 1 by 2 pi under root G by L. That means our natural frequency is directly proportional to under root G and inversely proportional to the under root square root of L. Hence when the length of a bob varies, the frequency also varies. Inversely proportional. So when we are increasing this square root of L in a simple pendulum, the frequency also decreases. Inversely proportional it is. Moving on to the next example of natural vibrations and free vibrations. Now the next example, that is a load suspended from a spring. When stretched or compressed and then released, start vibrating with its natural frequency. Its frequency is determined by the hardness, that is, or force constant K of the spring and the mass M of the load. that is f is equal to 2 pi under root k by m. In this case, frequency is inversely proportional to the mass, square root of mass. So as the mass vary, frequency also vary. The frequency will be different for the same load on different springs, and it will be different for different loads on the same spring. The same case happens for the tuning fork. When a tuning fork is stuck against a hard rubber pad, it vibrates with its natural frequency. The vibrations from longitudinal waves in air, which when reaches our ears, sound is heard. This sound is of a single frequency, pure note, that is one frequency only. Different tuning forks produce sounds of different frequencies. So in case of tuning fork, when we just put this tuning fork in vacuum, it will just vibrate throughout. Now the next example is the flute. The flute is made in the form of an open cylindrical air column, and sound is produced from a flute by blowing into a sharp edge, causing air enclosed in a tube to vibrate. When an air column in a flute is made to vibrate, it vibrates with its normal frequency, which is inversely proportional to the length of the air column. That is, frequency is inversely proportional to length. That means if length increases, frequency decreases. In a flute, the notes of different frequencies are produced by changing the effective length of the air column, with different holes in it are closed. Now, the nature of natural vibrations. The natural vibrations are the simple harmonic vibrations under the restoring force, the amplitude and frequency of which remains constant. That means the amplitude will not change with the time. Time is increasing, time is passing by, and hence you can see the amplitude remains constant up or down of the wave. This is one wave pointed with red marker. This is one wave. We also called it wavelength. The distance we called it as wavelength. The amplitude will not change. It will not decrease with the time. And frequency, here, what is frequency? We know that the number of waves in 1 second. Here we call it as natural frequency. And to calculate natural frequency, we know the formula, that is, it is the number of waves in 1 second. So suppose if we are considering a simple pendulum, so we have started our vibrations from this point, one of the extreme position. So we'll go to the other extreme position and again come back. So this is one wave. And in case of this displacement time graph, so once we started our journey over here, so this is one wave. So like this, number of vibrations in 1 second we can calculate. Suppose this stick, if I am just remove the number of vibrations, first I have applied a force and then slipped. So the number of vibrations in 1 second, that is how we can calculate the natural frequency. Okay. So the vibrations of a constant amplitude can occur only in vacuum. It is impossible to have vacuum here. So it is very difficult to realize such vibrations in practice. So to the motion, so the energy of the vibrating body continuously decreases, due to which the amplitude of the motion gradually decreases. Here a lot of frictional force is there. So if we just take an example of a simple pendulum, after a certain time it stops. But the natural vibrations and free vibrations only occur in vacuum, because once we are applying force and we left it in in the vacuum, and hence the body vibrates over there. Now we will discuss a question from the exercise 7b. Question number 10. In this question they have given a diagram like this, and in this diagram three different ways in which the string of length L in an instrument can be vibrated. So these are the way, first way, second way and the third way of vibrating of the string. Now in the first question they ask that which of the diagram shows the principal note. Now what is principal note? If the wave starting point and ending point forms of one wave, that is the principal note. See, in this we have 4 waves here, 2 here, 3. Similarly, the first one, diagram 1, shows the principal note. In the second question number B, they are asking which vibrations has the frequency 4 times that of the first. Here you can see in this principal note how many times it is divided. 1, 2, 3 and 4. Hence here the frequency will be 4f. So this third diagram has the frequency 4 times that of the first wave. In this wave we have frequency 1. Number of oscillations in 1 second 1. Number of oscillations here it is 4 seconds. In 1 second it is 4. So this number, figure number 3 has frequency 4. Now the next question, number C. Which vibration is of longest wavelength? Of course the first one, longest wavelength. Now the next one, what is the ratio of frequency of vibration in diagram 1 and 2? So first frequency is F, take out the ratio F1 by F2. For F, first figure the frequency is F, and for the second diagram the frequency is 2F. So F and F cancel each out and hence the ratio is 1:2. So like this they will ask you the question, you can explain in this manner.